So now we want to get into the final topic of multivariable calculus, which we're going to spend about a week on, and then next week we'll do the proof-based stuff. So this is multiple integration. So this is basically the integration equivalent to multivariable calculus, just like partial derivatives were the derivative equivalent for multivariable calculus. And we've kind of already seen a example of this when in Math Tools 2, when we were finding the volumes of different objects like revolutions of solids or solids of revolutions rather, and spheres and stuff like that. So it's going to be kind of the same idea here, where in that one, what we basically did was we found the area of a slice, and then we integrated that along the whole region. But with multiple integration, we won't necessarily be able to find the area of a slice just by using like the formula for a circle or something like that. Instead, the area of a slice will be given by an integral, and then we'll integrate that output over the entire region. Okay. So basically the idea will be you integrate in one direction and then you integrate in the other direction. So you integrate horizontally and then vertically, or vice versa, basically. So it's a pretty natural extension of what we were doing in those videos, and what we're going to end up with, at least in a two variable function, is the volume of a region. And in a three variable function, well, then it's kind of hard to picture exactly what we're getting, right? I don't even know what the word for volume in two dimensions we have area, in three dimensions we have volume. I don't know what it is in four dimensions, to be honest. I'd have to look it up, but we'd get whatever equivalent thing there is there. So for that reason, we're going to focus mostly on double integration, within three dimensions, two variable functions. But then at the end, we'll look at what this would look like for any arbitrary number of variables. And it's going to be pretty natural extension, just like it would be for partial derivatives, where you just have three partial derivatives if you have a three variable function. Okay. So we're going to break this up into different types of regions. So we're going to first look at integration in rectangular regions, and then in more general regions, and we're going to look at some regions that can be kind of tricky as well. So let's look at a quick example here of just like what this would look like graphically. Again, it's pretty similar to what we were doing with the spheres and the solids of revolution back in Math Tools 2. It might be a good idea to like go watch that video again, just to kind of get the idea, because I think it is simpler in that context to kind of grasp when we're working with like easy shapes, like a sphere, which is much simpler than something like this. But the idea is the same. So, say like we want to take some slice of this function, and we need to find the area of that slice. Because this is such a weird function, it's not just a nice circle or something like that. The only way we can find the area would be to integrate, right? So the integral of that, whatever the slice is, would give us the area of that slice. Then we would go ahead and integrate whatever that is vertically. Okay. So that's kind of the idea here. And you could do it in the other order too. In most cases, those are going to be the same thing. It's not always the same thing. We'll write down the conditions for that. Okay. But let's get into some of these formulas here. Or actually, I think I would like to just start with an example, which is just that function we were just looking at. I didn't say what it was, but you might have noticed it. It was f of xy equals 3x squared minus y. Now we want to find the volume of f over the region r equals 0, 2 cross 0, 2. Okay, so I mentioned that this notation is very common when we're talking in an integration context. So it's the same idea as when we were optimizing over a rectangle, right? This is technically a square actually, but so these are basically the x points right here, and these are the y points. Okay, so this is like the interval of x points, and this is the interval of y points. So if we wanted to find the volume, what we would do is, first we would just integrate this 3x squared minus y with respect to one of the variables, say x, over that region, so 0 to 2. Now, this does present a new issue, which we haven't seen yet, which is how do you integrate something where it's a different variable, right? And it's just like how we do it in partial differentiation, where you just treat that variable as a constant. The exact same thing here. We're just going to treat that variable as a constant. Okay. So here we're going to get x cubed minus, xy, right? Because y is a constant. And we're doing this from x equals 0 to x equals 2. So we're not just going to get a number in this case because we're going to have y in there still. But we're going to have 8 minus 2y. And that looks like it because the other points will be 0. And then we're going to take that function, the output there, and integrate that over the y points. Okay. So same idea as the sphere, the solids of revolutions, where first we find the area of a slice, then we integrate over the other part, except to find that area of a slice, now we have to integrate first. Okay. So this is dy. So this is going to be 8y minus y squared from y equals 0 to y equals 2. And so that's going to be 16 minus 4, and then all that's going to be 0. So we're just going to get 12. Okay. So if we write this all out in one line, what we did here was first we integrated this 3x squared minus y dx. And then we took that and we integrated that over y. Okay. So this is called an iterated integral. And the way we would typically write this is just the same exact way, except without the brackets here. Okay, dx, dy. So we have the innermost integral, and this tells us which variable to integrate with respect to first. This tells us what our first bounds are, so we work inside out. And then we have our secondary integral on the end. So again, that's called an iterated integral. Okay. So more generally, do we call this function f? We did. We would say that the volume of this function is given by the double integral. So we write two integrals over r of f of x, y. And then we say dA, where A is the area. So this is like with respect to the area. Okay. So this is just like the more general way to write it. It's not like the functional way that we'll actually find the integrals. That would be like how we're doing it up here, right? So, but first, a few theorems that I want to go to before we get into some more examples of how to integrate. So today we're just going to do rectangular regions. So I'll do a bunch of examples in the next video. And then in subsequent days, we're going to look at different regions. But this is the same general idea for all of them. But the regions can be kind of tricky to integrate over, so we need to look at how those work. So let's just go through some properties of these. And, most of them will be the same properties we've seen, but there are a few that are important to see in this context. So if we have the integral of f of xy plus g of xy dA, then of course we can split this up over addition. Okay, so f of xy dA plus the integral of g of xy dA, okay, over r. Okay. So we can still break it up over addition. We can still pull out a constant. Okay, so if we have some constant c, then there's no issue in pulling that out. Okay, and I mean, all of these properties are just kind of inherited by the fact that we're just doing two integrals. So why wouldn't we be able to do this, right? One property we had with integrals was that we could break it up into two. We could break one integral up into two integrals. Like if you had an integral from 0 to 10, for example, you could break it up from the integral from 0 to 5 plus the integral from 5 to 10. Same idea here, but the regions we're working with aren't so cut and dry, right? They're not just intervals anymore. Now they're sets. So we need a little bit more precise language. Okay, so if R is equal to S union T. So if you remember the union sign from intervals, it meant that we're joining two intervals together. So this is the same idea. We're joining two sets together. We're going to look at sets more in depth later. We don't need to know too much about it right now. Just basically, R needs to be able to be decomposed into two sets, S and T, which are separate, which is shown by this right here, which is that S intersecting T is the empty set. Okay, so this is the empty set. Okay, well, it's the set with no elements. So in other words, S and T do not share any elements in common. So, for example, if you have an interval like 1, 3, that's equal to the interval of 1, 2, union the interval of 2, 3, right? Where here, these two sets do not have any element in common, because this one doesn't have 2, this one does. Right, so same idea, but it's going to be a little more general because again, we're stepping, our domain now is in 2 dimensions instead of just 1 dimension. But one condition of this is that they can overlap on the boundary. Okay. Whoops. So let's say except and overlap on boundaries. Okay. Just like, these two are allowed to overlap on the boundary as well, because that one single point doesn't make a difference, right? The integral from 2 to 2 is 0. So it's kind of the same idea here, is that boundary is not really making a difference there. That whatever line that's on, that's going to have 0 area. So then, if this is the case, then the integral of fxy can be decomposed in the integral over s plus the integral over t. Okay, so same idea, maybe a little bit harder to execute though, because the regions are probably a little bit harder to break up than intervals are, right? There's a few more that I'm going to skip over that I think aren't really worth stating again, like the fact that if one function is greater than the other function, then the double integral is going to be greater than the double integral of the other function, right? That's just inherited from single integrals. The one that I think is pretty important is that if f of xy is equal to g of x times h of y. So this is an interesting one. So if f of xy can be broken up into the product of two functions, okay, then over the region, r is equal to xy, such that a is less than or equal to x is less than or equal to b, c is less than or equal to y is less than or equal to d. So this is a rectangular region specifically here. The double integral can be written as the integral of r of f of xy dA is equal to the product of the integral of a to b of g of x dx and the product from c to d of h of y dy. Okay. This is an interesting property for a few reasons. One, this idea that f can be decomposed into a function of x times a function of y is also seen in probability. When you look at a joint probability distribution function of two random variables, one way you can tell if those two random variables are independent is by this same property, that they can be broken up into, their PDFs can be broken up into products of each other. Okay. And to find joint probabilities, we often have to do double integrals. So this gives us a way to evaluate those. Okay. This actually is also the way that you can integrate e to the negative x squared, at least the definite integral version of it, which is kind of interesting. I won't go through the whole thing here because it involves a coordinate system change as well. But the integral of e to the negative x squared dx from, like, say a to b, the way that you do it is by setting this, say this is equal to like I or something. Then what you do is you square it. So you say I squared is equal to e to the negative x squared ab dx squared. And then you write this out as a product. Okay, ab e to the negative x squared dx times, you would need to change the coordinates. The most common way this is done is with infinity and negative infinity, so it doesn't matter here. So let me just write that instead. Okay. And then times negative infinity to infinity, and you usually change the coordinate here to dy. Okay. So you square it, so when you change the coordinate on the inside, it doesn't actually change because you're only multiplying the output of this integral, right? So the variable on the inside doesn't matter. So that's why we use a second one here. And then you use that property to put them back together as the integral from negative infinity to infinity, integral negative infinity to infinity of e to the negative x squared plus y squared dx dy. Okay. And then from there you change to polar coordinates, which is not something we went over, but it's actually not as hard as it sounds. It actually makes the integral pretty easy because this just becomes a single variable, which we call r. But this allows us to integrate that function over an interval, so like a definite integral version of it. And then we just take the square root at the end since we squared it here. So that's obviously of interest because that is in the normal distribution, right? And we spend a lot of time approximating this integral. It still just doesn't let you get an indefinite integral version because you do need the bounds here. But that's why, I would say that this is one of the more interesting properties for our purposes here. All right, last property I want to mention in this video is what's known as Fubini's theorem. Okay. So this is the theorem that allows us to switch the order of which variable we're integrating with respect to first. Okay. So this says that suppose f of xy is continuous over r, which is equal to what we just had it equal to, xy, such that let's just say x is in AB, y is in AB, or CD rather. Okay, same thing. Then the double integral of r is equal to the double integral of r fxy dx dy, and then we can bring in the iterated integral here, is equal to CD AB fxy dx dy, and that's equal to AB CD fxy dy dx. Okay. Being able to change the bounds of integration is extremely useful because there's some integrals that are way easier if you do one of the variables first, especially when we get into non-rectangular regions where our bounds might be variables themselves. So this is really important, but note the very strong condition, which is that it needs to be continuous, right? And of course, lots of functions aren't continuous. This can actually be weakened a little bit, which is it just needs to be bounded on R and discontinuous only over a finite number of continuous curves in this case, since we're in 2 dimensions. But just like find the equivalent in 1 dimension would be over a finite number of points. Okay. So, that we can weaken the conditions a little bit, but continuity in general is still a pretty strong condition, and it can only be discontinuous, again, over a finite number of places. So pretty much everything we'll look at, we'll be able to switch the bounds of integration, but just in general, you shouldn't take it for granted. Okay. People, when they tend to do a lot of double integration, you just kind of forget about it and you do start to take it for granted. But it is very important that those conditions are met. There's also a successor to this theorem called Tonelli's theorem, or sometimes they're combined called Fubini-Tonelli's theorem, or different sources always do different things, but Tonelli's theorem weakens the conditions even more. The condition here is basically that f is integrable, Riemann integrable. Tonelli's theorem doesn't even need that. It needs what's called a measurable function, which gets into measure theory, which, that's like a whole other topic. But the point is that you can weaken it even more. So most of the time you'll be able to do this, but it's just, something to keep in the back of your mind. If you're working with a really weird function, it might be possible that you can't do this.